Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, I will deliver my lecture on factor or causes controlling metamorphism part 2. In this part, I will proceed under the following heads: pressure, hydrostatic stress, differential stress, fluid pressure and fluid rock interaction. Hope it will be useful for you. Try to be regular in course. Pressure play an important role during metamorphism. It is assumed that pressure surface are parallel to the surface of the earth. Pressure increase with depth of burial, thus both pressure and temperature will vary with depth in the earth. So the change of pressure in rock is related to the change of position along the vertical space coordinate z extending from to the surface of the earth is the function of the acceleration due to gravity g and average density rho of the overlying material. We can divide the pressure into two types. First, hydrostatic stress or uniform stress. Second, diabatic stress or differential stress. Lithostatic pressure is the most important variable because most metamorphic reactions are to some degree pressure sensitive. Pressure is defined as the force acting equally from all directions. It is a type of stress called hydrostatic stress or uniform stress. If the stress is not equal from all directions, then the stress is called a diabatic stress or differential stress. If suppose we consider the P total equal to P load plus P fluid, lithostatic pressure is exerted by the overlying mass of the rock and the magnitude depend on the depth and the density of the rock column. P load, if we want to calculate, then we have to take the equation for the rock column. Say for example, like granite, basalt or pedotite, we know already the G equal to 9.8 meter per second square. If we know the height of the rock column, then we can calculate the pressure on a surface. For example, the acceleration due to gravity near the surface is small g equal to 9.8 meter per second square, and range of typical rock densities are granite equal to 2.7 gram per centimeter cube equal to 2700 kg per meter cube, basalt 3.0 gram per centimeter cube or 3000 kg per meter cube, pedotite 3.3 gram per centimeter cube or 3300 kg per meter cube. Using these values, a 1 kilometer column of the rock exert a pressure of granite, that is P equal to 2700 into 9.8 into 1000 equal to 264 into 105 Pascal equal to 264 bars. Lithostatic pressure is exerted by overlying mass of the rock and its magnitude depend on the depth and the density of the rock column. Knowledge of the depth lithostatic pressure is of paramount importance in making tectonic reconstruction. The relation between pressure and depth in the crust is given by the equation where P is the pressure, rho is the density of the rock column and H is the depth. SI conversion for the unit of pressure is the Pascal, where 1 Pascal equal to 1 kg per meter per second square. Geological pressure has been traditionally reported in bars or kilobars, and the conversion is 1 bar equal to 10 to power 5 Pascal equal to 0.1 megapascal equal to 1 kilobar or 0.1 gigapascal. The acceleration due to gravity near the Earth's surface is g equal to 9.8 meter per second square, and Range of typical rocks density are granite 2.7 gram per centimeter cube and basalt 3.0 gram per centimeter cube and petrotite 3.3 gram per centimeter cube. Using these values, a 1 kilometer column of rock exerts a pressure of granite, see on the screen, that is nearly 264 bars. Pressure is defined as force acting equally from all directions. It is a type of stress called hydrostatic stress or uniform stress. If the stress is not equal from all directions, then the stress is called a differential stress. If differential stress is present during metamorphism, it can have a profound effect on the texture of the rock. Minerals that crystallize or grow in the differential stress field can have a preferred orientation. This is especially true of the seed silicate minerals, for example, the mica, biotite, muscovite, chlorite, talc, and serpentine. These seed silicates will grow with their seed oriented perpendicular to the direction of maximum stress. Preferred orientation of seed silicate causes rock to be easily broken along approximately parallel sheet. Such a structure is called a foliation. The diatoric components of the stress that cause rock to fold, to form minerals, to align, porphyroblasts to rotate, it's produce the oriented fabric to the rock. The figure is a pressure temperature diagram depicting the range of conditions that are typically observed in metamorphism. The crustal environment where these pressure temperature conditions are likely to be realized, as well as melting curve for dry and wet granite and basalt. For reference, high P, low T metamorphism occur in subduction zone and in the area of rapid overthrusting of continent masses. Low P, high T metamorphism occur in region of high heat flow such as oceanic ridge, Iceland arc, and contact areoles. The large region of intermediate pressure temperature condition occur in continental collision orogenic belts. Fluids play an important role during metamorphism. Any existing open space between minerals grain in a rock can potentially contain a fluids. P fluids equal to PS2O, PCO2, PO2, PS2 plus PCH4 plus all possible gases or fluids, because these fluids play a very important role during metamorphism, because whatever the material, they can migrate through or within the fluids. The phase equilibria of the metamorphic rocks, the mineralogy and mineral chemistry are dependent to a first order on the partial pressure of fluid. Fluid migrates through rocks and transport heat and responsible for the deposition of ore bodies. Fluid trapped in a rock is useful for the study of fluid inclusion, because with the help of fluid inclusion we can find out the initial pressure and temperature condition during the trap of the fluid or during the formation of the metamorphic rocks. Within increasing pressure of metamorphism, the pore space in which the fluid resides is reduced and thus the fluid is driven off. Thus, on fluid will be present when pressure and temperature decreases. Fluid pressure is simple the pressure of metamorphic fluids. If the fluid is a pure species such as H2O, then the fluid pressure is equal to PS2O pressure, P fluid equal to PS2O. If the fluid is a multi-component mixture, then fluid pressure equal to sum total of the partial pressure of the different species, like P fluid equal to PS2O plus PCO2 plus PO2 plus PS2 plus PCH4 plus etc. Fluid pressure are generally believed to be equal to lithostatic pressure P fluid equal to P total in deep-seated recrystallization, but this is not always the case. For example, where P fluid less than P total have been well documented and are characteristic of the zone of brittle fracture in the upper crust. Some environment PF may be more than P total as a situation known as fluid overpressure and responsible for trigger faulting. In dehydration reaction, the equilibrium temperature is controlled by the major concentration of water X(H2O) in the fluid phase. The equilibrium is shifted towards lower temperature with decreasing X(H2O) in the fluid phase. In the case of decarbonation reactions, the equilibrium shifted towards the higher temperature with increasing molar concentration of XCO2. A typical example is the reaction see figure on the screen. Calcite plus quartz give rise to wollastonite plus CO2. It is clearly observed from the figure the equilibrium curve shifts towards the right with the increasing XCO2. The equilibrium in the case of reaction involving fluid has been observed by Greenwood 1962. Fluid rock interaction. Fluid rock interaction is very important during metamorphism because the rock interact with fluids and moreover the OH bearing phases in minerals like amphiboles, mica, clay, etc. play a very important role during high grade metamorphism. When prograde metamorphism exists, then these fluids are driven out and the rock is almost dry. Chemical reaction during metamorphism and formation of new mineral is extremely a very slow process because the minerals take a long time to recrystallize. Therefore, the pressure and temperature crystallization all are related with time, and that geologically may be a million years. I will cover this topic in 3 parts. In part 1, I will proceed under the following heads: causes of metamorphism and temperature, geothermal gradient, geotherm in the plate tectonics. Hope it will be useful for you. Try to be regular in course. We know that metamorphism takes place when a rock is exposed to physical or chemical environment that is significantly different from that in which initially formed. These includes temperature T, pressure P, shearing stress, fluid pressure or chemically active fluid, fluid rock interaction and composition, the nature of the fluid phase and state of stress. Fluid play an important role for the transportation and migration of material and even for the deposition of ores. Initially, mineralogy, chemistry or changes in chemistry or mineralogy is also an important part of metamorphism. It will see the bulk composition also play an important role during metamorphism because if a limestone and gravel or argillaceous rock is subjected to the same pressure and temperature, then marble and schist rocks are formed, so that composition also play very important role during metamorphism. The rock that are metamorphosed may be igneous, sedimentary or already metamorphosed rock, and their recrystallization is largely isochemical without having undergone chemical changes except loss of fluids. The reacting phases in a rock are solids and commonly a pore fluids, including the dissolved material in the fluid and migration of fluids, all of which impart changes in the mineralogy, mineral chemistry and even some cases bulk chemistry of the rock. All these factors can be loosely regarded as external agents that act upon the rock and effect metamorphic changes. The other important factors to consider in the bulk composition of the rock is important to recognize that some set of external factors will affect different changes in rock of different bulk composition. The temperature play a very important role during metamorphism or during the process of metamorphism. Changes in temperature are probably the most common cause of metamorphism. Normally, we measure the temperature in degrees Celsius, and in case of thermodynamic calculation, the temperature Kelvin K equal to 0 degree centigrade plus 273.15. The temperature increase with depth, and the rate of increase of temperature with depth is called geothermal gradient. The temperature increase in earth crust through mantle processes, or in other words, we can say through the convention of mantle current. Similarly, the radioactive elements also play an important role to increase the temperature, and the geothermal gradient also increase the temperature. The temperature increases the reaction rate, and usually during static environment, the grain size is bigger during crystallization. Is particularly true for the grained rocks in a static environment because shear stresses commonly act to reduce grain size. It also causes liberation of volatiles from the hydrous phase and also the dissociation of the components of the fluid phase. An ordinary geothermal gradient is modified by several factors, some of which are: first, rapid accumulation of sediments; second, rapid tectonic sinking of the metamorphic complex; third, endothermic reaction in metamorphism; and fourth, intrusion of magma. Mayasiro in 1973-86 has estimated the geothermal gradient for the different barrick type of regional metamorphism to be low pressure less than 25 degrees centigrade per kilometer, medium pressure around 20 degrees centigrade per kilometer, higher pressure about 10 degree centigrade per kilometer or less. See figure on the screen. The intrusive emplacement at shallow depth can impose a geothermal gradient as high as 100 degrees centigrade per kilometer or more on the adjacent rock. Granite begin to melt at 625 to 650 degrees centigrade and basalt at 850 to 900 degrees centigrade between 2 to 3 kilobar fluid pressure. So, upper limit of strictly metamorphic process might be considered to be 900 to 1000 degrees centigrade. The increase, rather change of temperature dt and with vertical heat influx thickness dz would give local geothermal gradient or geotherm, that is dt divided by dz. Upward heat flux or heat flow q measured as watt, that is meter per second per watt, is proportional to the thermal gradient, that is q equal to k dt divided by dz, where k is the proportional constant known as the conductivity of rock, k is the amount of the heat conducted per second through an area of 1 meter per square second, z is the depth measured downward from the surface. Perturbation of conductive geotherm. The rock of the crust and mantle are very poor heat conductors. Consequently, the heat diffusion is very sluggish. However, local heat addition perturb the conductivity geothermal gradient. See figure on the screen. The factor responsible for perturbation of a geotherm are: first, fluid circulating through rocks undergoing metamorphism perturb the geotherms corresponding to the gradient and hence perturbing the geotherm. Second, magma from upper mantle or from the crust are powerful agent of heat transfer and result into the rise of isotherms and hence perturb the geotherm. This happen also when magma underplate or interplate the continental rock as during the formation certain gamma-like terrain. Third, ductile shearing can also perturb the geothermal when the intensity of shearing and sheared and speed of rock movement along the dislocation are high, particularly seen in the development of pseudo-trachytes. The nature of the geotherm in PT space is largely controlled by the rate of vertical subsidence, that is a small v, of the lithologic units and also governed by the rate of convergence, capital V, and dip angles of the litholog's units. The relation is expressed by the equation small v equal to V sine alpha, that is subsidence of the cold hydrated oceanic lithosphere during plate tectonic cycle will give rise to high P and low T gradient, which is marked by the downdraft of the isotherms. See figure on the screen, which is responsible for the rock like blue schist facies, glaucophyll lawsonite facies. The subduction along the trench produces heat increase of T due to shearing in the upper oceanic crust. This gives rise to high pressure and high temperature rock like eclogites that are usually associated with blue schist, as in the Franciscan belt formed as a result of subduction of the Pacific plate under the North American plate. The continental material increases in thickness due to shortening, structural duplication, and subduction rate so down, finally blocking the burial of the continental plate. This decreases the slope of the geotherm, which now becomes a high to moderate temperature due to radioactive heating of the structurally thickened crust. This Barrovian type geotherms and metamorphic range from geolite, green schist, epidote amphibolite, gamma-like facies. The above account give a brief resume as to how geotherm changes from high P, low T to intermediate P, high T, and finally to medium pressure to high T environment during a single period of orogeny. The following metamorphic phases were usually associated with a different plate tectonics setting. The sequence of phases observed going down the subduction zone is geolite, prehnite, pumpelite, blue schist, eclogite. In contrast, the sequence of phases encountered going down in the Iceland arc is geolite, prehnite, pumpelite, green schist, amphibolite, gamma-like. Dear student, today in this lecture we have discussed about the factor controlling of metamorphism part 1. I have covered this topic under the following heads: causes of metamorphism and temperature, geothermal gradient and geotherm in the plate tectonics. In my next lecture, I will cover pressure, hydrostatic stress, differential state, fluid pressure and fluid rock interaction. For further studies, please read the textbooks, references and links given in the text.